That we did in class this quarter, we first looked at the flight of a classical projectile. And classical projectile motion is characterized by constant velocity in the horizontal direction, as can be seen on the delta x versus t graph. It's a linear graph, the solid line here, indicating that the horizontal velocity is constant. The vertical acceleration is also constant, as can be seen on the y velocity versus time graph, the constant negative slope of 9.8 meters per second squared. And the trajectory of the projectile as a result of the constant acceleration vertically and the constant velocity horizontally is a perfect parabola, as can be seen on the delta y versus delta x graph, which shows the trajectory of the projectile, the solid line. When air resistance is present, things change. The horizontal velocity is no longer constant because the air resistance is pushing backwards on the projectile, as can be seen in the force diagrams here. Air resistance always acts in opposition to the direction the projectile is moving. So as it's moving up and to the right, air resistance will be down and to the left. When it gets to the top and it's moving to the right, the air resistance will be to the left. And on the way down, when it's moving down and to the right, the air resistance will be up and to the left. So when we look at the vertical motion, at the beginning, because the air resistance is down in the same direction that the force of the Earth is, we get a little steeper acceleration, more than 9.8 meters per second squared. When the projectile gets to the top, then the air resistance isn't pointing up or down, it's just pointing sideways. So it continues to slow horizontally, but there's just the force of the Earth pulling down, so the slope of the velocity versus time graph at that point will be the usual negative 9.8 meters per second squared. As the projectile begins to fall and picks up speed, the air resistance gets bigger and bigger, and now it's pointing upward, and that balances partially the force of the Earth downward so that the acceleration becomes less than negative during the last part of the flight. The projectile's trajectory changes as well. It doesn't go as high or as far, as can be seen on the delta y versus delta x graph here, the dashed line, not flying as high or as far horizontally as the classical case. For my project, I launched a spatula. I threw it by hand over a 2-meter tall stick that we used for scaling in the video. Before I could mark the points on the video, though, I needed to know what the center of mass of my spatula was. Or not the spatula. This is going to be my spatula. So my spatula is shaped kind of like this, and I found the center of mass by hanging it from several places on the spatula and dropping a line vertically below the hanging point. Where those lines crossed was the center of mass. For the spatula, it was right about here in the bend of the spatula. And that's the point that I marked in the video. To shoot the video, we used a high-speed camera, a Casio EX FC100, which shoots at 210 frames per second. And then we edited the movie in iMovie to cut out all the parts where the spatula wasn't in flight. And then we exported it as a QuickTime movie and imported it into Logger Pro to analyze. There were about 300 frames in the video, and we wanted about 30 frames that were marked, so I marked every 10 frames in the video. Once I did that, then I created 5 graphs, 4 of which I have on the board here. The first is the delta x versus t graph. This shows the horizontal position of the projectile as time goes by. This graph was not linear. It slowly curved and flattened out. So I used 3 different slopes on the graph. The first slope was 2.556 meters per second. That's the velocity near the beginning of the flight. The middle one is 2.336 meters per second, and the last one's 2.258 meters per second. You can see that as time goes by, the projectile's horizontal velocity is decreasing. You can also see that on the Vx versus t graph. This shows the x velocity, and it's decreasing slightly as time goes by. The slope here would be the acceleration in the horizontal direction, which would be 0 for the classical projectile, but not for mine. Also, graph the vertical velocity versus time. And this one, I also split into 3 sections. The middle section, I centered right around velocity 0, because that corresponds to when the projectile is at the top of its motion. And then I used the pieces that were left over before, which would be the rising part, and after, which would be the falling part of the projectile's motion. What I saw was that when the projectile was rising, the vertical acceleration was more than 9.8 meters per second squared, so negative 11.45. When it was near the top of the motion, the acceleration was negative 10.3 meters per second squared. Only a few percent more than the 9.8 meters per second squared. And then in the last part, when it was falling, the acceleration was less than 9.8 meters per second squared. And again, that goes back to the forces that are acting at the beginning. The air resistance acts in the same direction as the Earth while it's rising, so that gives a steeper slope. And when it's at the top, only the force of the Earth is pulling down, so the slope is the same as in the classical case, about 9.8. And then at the end, the air resistance balances part of the force of the Earth. So we get a smaller acceleration than the 9.8 meters per second squared. I also created a delta y versus t graph, but I didn't display that here. The results there confirmed the same things that we saw here with the accelerations. On the delta y versus delta x graph, the solid line is a parabolic fit for the first 8 or 10 points here, and that sort of predicts what the path of the projectile would be if air resistance didn't act throughout the motion. The dots are the actual path that it took, and you can see that it didn't go quite as high or as far as the classical, or the projected situation without air resistance. So when we compare these back to the classical and the air resistance cases, what we see is that on the delta x versus t graph, it very closely resembles the curved path for the air resistance. And same thing on the Vy versus t. Starts off steeper, ends up less steep at the end. And the delta y versus delta x doesn't go as high or as far. And again, the forces that are acting during the course of the flight, air resistance is always acting to the left. In other words, slowing the sideways motion, because the projectile is moving first up and to the right, then just to the right at the top, and then down and to the right at the end. So the air resistance acts down and to the left at the beginning, just to the left at the top, and up and to the left as it's falling. Since it's always acting to the left, it's always slowing the horizontal motion. And since the air resistance changes direction from down to up, it changes the acceleration in the way that was described before. Steeper, more acceleration at the beginning, 9.8 in the middle, and less acceleration at the end. Sources for error in conducting this, there are several. The first would be locating correctly the center of mass on the spatula. If I didn't know where it was exactly, it would be hard to mark it correctly on the video. Sometimes the spatula was turned at odd angles in the video, and that made it difficult sometimes to figure out exactly where that point was in the two-dimensional video, since my spatula is three-dimensional. So marking the position, even if I knew right where it was sometimes an issue. And then finally, scaling the video. If I couldn't see the ends of the 2-meter stick well, it would be hard to scale it perfectly. There's also an issue if the spatula didn't fly directly over the 2-meter stick. If it were closer to the camera or farther from the camera, that would affect the scaling would be off as well there. Finally, the questions that I had for further research, and I have no idea what Carly meant by this, so I'm just going to say, what allows for air resistance? Thank you very much.